I have to entertain a large group of visiting Japanese at dinner tonight. I'm going to have to come up with some suitably exotic and romantic story as to how this happened. I'll be thinking hard all afternoon to come up with that. Is this thing on? Huh. It was on a minute ago. Oh, there we go. Okay. All right, we're doing mechanical properties, and systematically we talked about elastic deformation. Today we're going to focus on plastic deformation, and then we'll turn to fracture and how things break. Just to remember, you can summarize the important mechanical properties of a material in a tensile test, in which the engineering stress-strain curve comes out looking something like this. Back here at low loads, you get elastic deformation. Stress is linearly proportional to strain in a typical structural metal, and the strain is recoverable. You load the sample up, let it go, it snaps back into its original configuration. When we pass the yield strength of the material, which is whose definition we discussed, Sy, and the curve goes nonlinear, you begin to get stable plastic deformation. Now if you stop the test and relax the sample back, it will relax in parallel to the original elastic curve, so you end up with some net plastic deformation. That plastic deformation is stable in the sense that it occurs more or less uniformly throughout the bar. Now I'll give you a somewhat finer discussion of what uniformly means in a little while, but essentially from a macroscopic point of view, you will see this bar elongate without changing its shape. That will continue until we get to the ultimate tensile strength, which is the peak of the curve. At that point, what happens is the plastic deformation becomes unstable. It concentrates here, and in neck in the specimen, all the deformation starts happening right there, and the specimen pulls apart. Now this, of course, is the engineering stress-strain curve, where our measure of area for stress is the original area of the specimen. Our measure of length for strain is the original length of the specimen. Of course, as deformation proceeds, the cross-sectional area and the length change, and it is, from a scientific point of view, better to talk about the true stress-strain relation. In engineering, we tend to use the engineering stress and strain because certain features of the diagram, for example, the ultimate tensile strength, are obvious in the engineering stress-strain curve, and as we discussed last time, are less obvious in the true stress-strain curve. In fact, they're not obvious at all. You do not have a maximum in the true stress-strain curve. The true stress just continues to increase until the sample finally breaks. Okay, plastic deformation is that second regime. In what sense is it important in engineering? Well, from the perspective of design, virtually every engineering device is designed so that we don't have plastic deformation. You don't want the dimensions of your devices changing while they're in operation, your automobiles or your engines or whatever they are. So the yield strength must be known and understood, because that is the design limit is stated with respect to the yield strength in virtually every design code there is. So one of the first important things about plastic deformation is to understand it well enough to avoid it in setting up engineering devices. The ultimate strength is a critical parameter in design, because that tells you the total load that a piece of material can take. If you're designing a building, for example, you have beams in the building. The beams have a certain cross-section. Certain loads are applied, for example, by the wind, which is often the major load on a building structure. Earthquakes, of course, are a special case. And you do not want those beams to break. The ultimate tensile strength tells you what the maximum load can be before that happens, so it's very important. Plastic failure, necking, and fracture. The engineering use of plasticity is largely in manufacturing. Most engineering devices, as part of their manufacture, metal devices anyway, are deformed into shape. Even fairly heavy things like roller turbines, great big things like that, are forged from billets into their final shape. Automobile bodies are sheet formed into their final shape. And that forming, that manufacturing, is a very large part of the cost of the vehicle. The formability of, for example, the sheets that are used in automobile bodies not only determines a lot of the cost of the automobile body, but also determines what the designer can do in terms of sexy designs for the car. Because sexy designs almost always require certain contours that are difficult to form, difficult to make, and therefore you have to have very formable materials in order to do that. So manufacturing formability is a big issue. Finally, in service, failure resistance and failure analysis. The plastic deformation of a material is really what gives you your margin of safety between the elastic deformation you design to and the ultimate failure. And in fact, we'll see that when we get to fracture, but just from the stress-strain curve. What's called the strength ratio, the ratio of the ultimate strength to the yield strength, is a design parameter that is often specified in specifying structural materials. And the reason that's done is that this is your cushion. If you do happen to have loads that exceed the yield strength, you don't want the material to deform at all, but if it does deform, you don't want it to break. And this is your cushion, the margin above the yield strength that you have to work with in which the material will not come apart. So very often in structures and engineering devices, part of the specification of the steel that's used to construct them is the strength ratio, the ultimate to yield, which measures the cushion you have against some kind of overload event on the material. So those are all important. There are several mechanisms of plastic deformation. We're only really going to talk about one. We talked about it earlier in the course. We'll talk about it again, because that is the most important in a usual engineering sense, and that's plastic deformation by the motion of dislocations. But there are other ways that you can change the shape of a material. For example, by diffusion. If you take any material and just let it sit around under load, the atoms will reconfigure themselves over time to adjust to that load. There will be what we call creep, diffusional creep, goes on in any material at any time because of the motion of atoms in response to the applied stress. One place that you can see that, if you ever happen to go to, I talked about windows recently, but if you go to a building where there's been a glass window that's very, very old, it's been in the same place for a century or more, and you look at it, you can actually see that the window pane will be thicker at the bottom and thin down at the top. And that's creep, diffusion of the material inside the glass in response to gravity. It's deforming its shape. If you go to buildings that have been around for a long time, particularly the ones that are old enough to have lead pipes, you'll see an external pipe running along, and you'll see it bowed in between its supports. That too is, in many cases, a diffusional creep kind of phenomenon. So I can get, in fact, you can prove thermodynamically that there is no such thing as a solid. You know, the definition of a liquid is that it takes the shape of its container. So will a solid if you give it enough time. Because thermodynamically, the second law tells you the evolution of the material will be toward a shape that is most compatible with the applied stresses, which will be fitting its container. And there exist mechanisms, such as diffusion, that may take more than the lifetime of the universe to accomplish that, but will eventually accomplish that and cause the solid to behave like a liquid. So in a sense, because of these mechanisms, there's no such thing as a solid. We don't have to worry about that most of the time, but it is true. Structural phase transformations. There are a number of situations in which under load, particularly if we have a material that is frozen in some metastable structure, under load, we may trigger the transformation of that structure. A place in which this is fairly widely used is in actually the formability of certain kinds of steels, for example, for automobiles, because I can get a significant amount of extra plastic deformation by taking the steel and freezing in the high temperature FCC phase and then letting that flip to the body-centered cubic phase under load, because there's a deformation associated with that transformation, and that deformation can be used to enhance the plastic deformation of the formability of the material. The most extreme example of that, which you've probably heard about, is in shape memory materials. There are a number of materials, nitinol is a classic example, which, quote, preserve the memory of shapes they previously had. So you can take a nitinol, the classic thing is you take a nitinol wire, you use it to spell out the name of your girlfriend, cool it down, decide you want a new girlfriend, heat it back up, and it goes back to its original shape. So it erases itself. These things are useful in engineering devices. So, for example, suppose you want to be able to operate a switch on the moon. One way to operate the switch on the moon is to have a shape memory device which will change shape if heated, and you just have a little heater. So all you have to do from the Earth is activate the heater. The shape memory device changes shape. Another place that's used is in stents in the human body, where you may want to put a device into the body, and you want it to be one shape so you can get it in, and then you want it to be another shape so that it will perform its function. You can use shape memory always for that purpose. And the basis of these are structural phase transformations. What you do is you take the high temperature phase, use the phase transformation to deform it, not a low temperature phase, so that the shape change has come about through the deformation, through the phase transformation. Well, if you heat it up again, that transformation can reverse itself. And since all of the variants that gave you the shape change, all the different ways the crystals are oriented that gave you the shape change, all come from the same parent phase. When you heat it up again, they'll snap back into the same parent phase, which means you go back to the original structure. And that's how shape memory always works. So that's a use of transformation-induced plasticity, often just referred to as TRIP. Finally, grain boundary sliding. We can deform a material by having grains or groups of grains literally slide over one another. This can be a fairly important mechanism at high temperature. And in fact, it's a dominant mechanism of what's called superplasticity. There's certain fine-grained materials that you take them up to high temperature, put them under load, and they will deform like bubble gum, even though they're fairly decent structural metals. Cool them back down again, they freeze in the new shape. This is a phenomenon known as superplasticity. There's superplastic aluminum alloys, superplastic lead tin, bismuth tin can be made superplastic fairly easily. And in the case of aluminum alloys, superplastic forming is actually used to make certain complex shapes that are used in aircraft, for example. By taking high temperature, using the superplasticity to get some dramatic change in the shape of the part, then you cool it down again and use it back to a good structural metal. So these are the mechanisms of plasticity. Other than this discussion, the only one I'm really going to talk about is dislocation plasticity. And that, of course, continues the discussion we had much earlier in the course. Remember, I showed you a movie back then. I warned people, much better movies. I was going to get one this morning, but unfortunately I was getting my head checked instead, so I didn't. But I showed you a movie earlier in the course in which we just indented a piece of aluminum, and you saw a shower of dislocation. Dislocations emerge, and finally a shower of them appear as the indenter penetrated the material. This is done in the transmission electron microscope. And this is just a sequence of steps during that indentation in which an increasing number of dark lines appear, and these dark lines are the dislocations, the linear defects in the material that control plastic deformation. Here's another example that I did pull up this morning, but I haven't had it in a paper we sent out about a week ago. This happens to be titanium with a little bit of oxygen in it. And this is in situ pillar compression. What you do is you make a nanopillar. You'd like to be able to study the interactions of dislocations directly in real time. So what we do is we take a nanopillar and take a device in the electron microscope that compresses the nanopillar. You can see the top has been squashed here. And then you can see the evolution of the deformation as the pillar compresses. Here you see dislocations having in the material, they tend to move along 45-degree lines where the shear is maximum. We'll talk about that in just a moment. Particularly as you get the solute content up, so it becomes harder to move the dislocations. The material becomes quite a bit stronger. You get the deformation produces real tangles of dislocation, such as you see here. This is the phenomenon of dislocation hardening or work hardening that we'll talk about in just a minute. But we can now observe the behavior of dislocations and follow it. We can do both pencil tests and compression tests in the transmission electron microscope and actually see what's happening. And that's done on a regular basis in Andy Miner's group up at OBL. Plastic deformation happens in shear. Now suppose we have any state of stress or strain that you want. We can always just break it up into a sum of two kinds of well, in this case, stress, into a hydrostatic stress, which is the same in all directions, and into a shear stress. The hydrostatic stress is not trying to change the shape of a material. If I take a ball and compress it, it remains a sphere. If I'm compressing it hydrostatically, nothing changes. It is the shear stress, and there would really be three different shear stresses since I can use any set of two planes here. It's the shear stresses that are changing the shape of the material. And it's also the shear stresses, as we discussed earlier, that drive the dislocations, that cause dislocation plasticity. Remember when we first discussed dislocation, here's an edge dislocation in a simple material, which you would make by making a cut in the material, slipping the top of the material over the bottom of the material by the Burgers vector B, and then sealing it back up again. When you seal it back up again, if the top and the bottom match perfectly, as they will, if B is a lattice vector, then the only defect that's left is a line of compressed material here at the edge of the region that slipped. And that's a classic edge dislocation. Remember we talked about edge dislocations, we talked about screw dislocations, and general dislocations, and what they look like and how they might move. Dislocation motion causes a shear strain. Shear stress is required to drive plasticity. That tells you something interesting. Even if you test a material in tension, one of these tension machines, so you think you're pulling it to elongate it, the actual deformation that is going on in that material is not driven by tension, but by the shear stress that tension imposes. And I'll talk about that in just a minute. The most general dislocation, well, let's just imagine a dislocation loop here. The dislocation bounds an area that slipped. So you have a little circular dislocation, a dislocation loop. That dislocation loop would be created by taking everything above the loop and shifting it in the plane with respect to everything below the loop by the vector B. So the dislocation is just the boundary of the region that is slipped. Now, I won't go through the mathematics. It's pretty easy to show that the force that acts on that dislocation, first of all, if I put a shear stress on the material, the dislocation will try to move. It's going to try to move so to expand the area that's been sheared. And you can do a simple energy balance to show that the force on that dislocation, it's in the notes, is tau B, the shear stress multiplied by the Burgers vector, and this is the component of the shear stress acting in the direction of the Burgers vector. That force always acts normal to the line. Okay, the Burgers vector is a constant vector in the interior of this region. The force that acts on the dislocation is the shear stress in the direction of B multiplied by B. The direction in which that force acts is always perpendicular to the dislocation line. And the easy way to see that is that the only way the force can do any work on the material is to change the area over which slip has occurred. If the area of slip doesn't change, then no work is done. If the force does nothing but rotate the dislocation without expanding or contracting the loop, then there's no shear in the material, no change in the state of shear, and therefore no work. The only way you can get any work is to change the area of that loop. And you change the area of that loop by displacing the boundary of the loop normal to itself. So the force is tau b, and it always acts normal to the dislocation line, whatever the dislocation shape. If we assume a set of dislocations that have the Burgers vector b, and if you let them move an average distance, del x in the material, some tiny distance, then you can show that if rho is the dislocation density, that's the line length per unit volume, then the shear strain that's accomplished by this array of dislocations with density rho, Burgers vector b, moving average distance dx, the shear strain is just rho b dx. So we get a fairly simple relation between the movement of the dislocations and the shear strain that they accomplish. Okay, how do we get a tensile bar to deform? Since the tensile test is kind of our basic test, we know that plastic deformation is driven by shear, not tension, and we have to have dislocations moving to get that plastic deformation. So how does that connection get made? It gets made in the following way. Suppose I have here a cylindrical bar, and suppose I pull on that cylindrical bar with a tensile stress sigma, which is my load divided by the cross-sectional area of the bar. Well, the area we're talking about there is the perpendicular area, like the top face of the bar here. If I focus my attention on any other plane that is tilted with respect to the axis of the bar, and I look at the components of the force acting on that plane, if this plane is tilted with respect to the axis of the bar, there will be a component of that force in the plane, and that gives rise to a shear stress on that plane. You can actually fairly easily calculate what it is. The shear stress would be the projected force on the plane, this plane I've shown here, divided by the cross-sectional area of the plane, this plane here. The force, if this plane has a normal that's angled at an angle theta to the axis of the bar, then the force in the plane, the component of the force in the plane, is just the total force on the bar multiplied by the cosine of phi. Cosine of phi. Now, the direction of the force in the plane at angle phi will be p times the cosine of phi, as I've shown here in the diagram. The area of the plane will be larger than the cross-sectional area of the bar. And in fact, the area of the plane can be easily shown to be a over cosine theta, where theta is the angle between the normal to the plane and the axis of the bar. So we just plug in those two numbers, and we get that if we have an applied stress sigma, then the shear stress in the direction phi on a plane angle theta to the normal is just sigma times the cosine of theta times the cosine of phi. The maximum value that this can have is when both theta and phi are equal to 45 degrees, in which case cosine theta cosine phi is 1/2, and tau is sigma over 2. If I have any other angle in this plane, then tau will be less than sigma over 2. So anytime I put a tensile load on, if I look at any plane angled to the axis of the cylinder, there will be a shear stress acting in that plane. Now let us suppose that the shear stress required to move a dislocation is the critical resolve shear stress tau c. Well, nothing is going to happen on that plane until the shear stress that we get from putting on the tensile stress becomes equal to the critical stress tau c. So we load the bar up, and what causes it to begin to deform is when the shear stress on the most favorable plane for glide reaches the critical value. So you load the sample in tension, that builds up the shear stress on all the planes. The force required to move a dislocation is going to be different depending on which crystallographic plane we're talking about. And when we get tau greater than tau c on the most favorably oriented and structured plane, then the material begins to yield. So the yield strength, sigma y, is the strength at which tau is greater than or equal to tau c on the most favorable plane for the dislocation to move. We put on a tensile load, the response of the material is a shear deformation, and the connection between the two is given by this simple formula here. Yielding under tension, tau must be greater than tau c on the most favorable plane, so the yield strength is always greater than or equal to twice the critical resolve shear stress. Notice that the critical resolve shear stress is the material property, not the yield strength. The yield strength is a derived property. If this bar happened to be a single crystal, and if the single crystal was such, like a face-centered cubic crystal, where the close-packed planes are the easy planes for dislocations to move on, then as I change the orientation of the stress with respect to the crystal, I will see the yield stress go up and down. It's going to be, the yield stress will have its lowest value when the close-packed plane, the 111 plane, is exactly 45 degrees, because that's the favorable plane, and that's where tau is equal to sigma over 2. So the lowest value of sigma y will be 2 tau c. If I use any other orientation of the crystal, the 111 plane is no longer optimally oriented with respect to the load. And as a consequence, I'm going to need more stress because of the yield. So if you test the yield strength of a single crystal, which is not what the problem we ordinarily face in structural materials, which you do occasionally, particularly if you're making things like nanostructures and thin films on microelectronic devices and such things, then the yield strength depends on the orientation that the crystal has. Even though the material property that governs yield strength, the critical resolve shear stress, is always the same. Well, how do we get tensile deformation by slip? The slip occurs on a plane that's angled to the tensile axis. So you pull on tension, and you get slip. Notice that if I slip on a plane, the material actually gets longer. Well, in the example I showed you just a few minutes ago, here we're pushing down on the plane, so the pillar's getting shorter. And here you see the slip, you can kind of see fuzzy lines at 45 degrees. And you can see this thing has been offset a bit. This top has slipped. And because it has slipped, the height of this pillar has gotten shorter. You can see that same process kind of starting here. So you get deformation by slip at an angle to the axis of loading if you're loading in tension or compression. And this is how it happens. Of course, in a real material, it's polygranular, so you get all kinds of slip planes. Even in a single crystal, you'll activate many slip planes, and they'll tend to be in